Okay, so I think we are recording now, and we'll see what happens at the end of this. So we are talking about tests for a population mean, and we are actually going to try to cover two parts today since we missed yesterday. But it should be pretty easy because they're really, really similar. So tests about a population mean, ignore the day one. This is section 12.1. Tests about a population mean, section 12.1. So first thing we need to talk about is how to read a z-table. So, oh, my battery's low. Let's look at our t-table again.
If you're watching the video, please get out one of the
Laminated t-tables
T-tables
from the drawers.
from the drawers.
Page 7. Oh, look at that. I counted perfectly.
Here
And I
are
didn't count at all. I just got really lucky. All right, so if you are looking at your t-table, that's okay. You can keep an extra. Then I would like to know what critical value, Gesundheit, T star from our t-table, which is called table B, this laminated copy, has degrees of freedom 11 and a probability of 0.05 to the right of T. So what we did before for our confidence intervals was look at the very, very bottom for that confidence level, and then we just went up to whatever we needed. Now we're reading the table the real way. At the top, it has the tail probability. And if you look at your picture at the top, I don't think I have my picture on top here. The picture at the top of the t-table shows it is shading which direction? To the right. So it's already looking at areas to the right. Like we changed this z to an absolute value, we made it that positive version. That's what they're always doing on here is looking to the right. So I find my degrees of freedom 11, and I trace that over to a probability of 0.05 to the right, which would be right here, because here's my tail probability, 0.05. So if I did not have that inverse t function on my calculator, or program that I gave you if you guys have a TI-83, or if your calculator happens to die when you're taking your AP test, then you can still use the table to find that T star, that critical T value, okay? In a test, though, we're not using it in our math. We're just going to use that as a comparison for our P value. But we still do need to be able to read the table just in case your calculator dies. So let's try the next one. How about this? What critical value, T star, from table B has n equals 18 and a probability of 0.9 to the left? So two things I changed here. What did I change?
It's not degrees of freedom anymore.
It's not degrees of freedom. So if n is 18, then what is the degrees of freedom? 17 degrees of freedom. Should have said what are the degrees of freedom, okay? And then if this is 90% to the left, what does that mean?
To the right is
There's 10% to the right, yeah. So I need to use that column with the 0.1 at the top. And degrees of freedom 17. So we trace over, and we've got this value 1.333 for our T critical. Okay? One more thing with the t-table. What if we're testing the null hypothesis that mu equals 5 versus the alternative mu is greater than 5 based on a sample of size 20 and get a t value of 1.81. Find the p value of the test. So our alternative hypothesis is greater than. That's good. That's what the chart is giving us, right? Is to the right. If our sample size is 20, then what are our degrees of freedom?
19.
19 degrees of freedom. So for our 19 degrees of freedom, which is way down here, I trace that across, and I'm looking for our T of 1.81. Now that's not going to be exactly on the chart, but I do see it's between these two, meaning my probability is between these. So I can't say for sure my p-value is some number like I can if I use my calculator. But I can say for sure that the p-value is between 0.05 and 0.025. So I could say 0.025 is less than my p-value is less than 0.05. So no matter what, well, I guess not no matter what, assuming that the significance level is our standard 0.05, 5% significance, 95% confidence, then I would reject because my probability is less than 0.05. The p is low, the whole must go. We've got to get rid of that null hypothesis of our p-value smaller than alpha, our significance level. Okay. What if I change our alternative hypothesis to not equal to? So we're testing the null that the mean is 5 versus the mean is not 5 for our alternative based on a sample of size 37 and obtain t equals negative 3.17. Find the p-value of the test. So lots of different things in this one. What do I have to do?
Degrees of freedom.
I do need my degrees of freedom.
36.
36 degrees of freedom, right?
Mhm.
Uh-oh. 36 is not on the chart.
Give you a 30.
Yes, because
Less degrees of freedom.
always have to go down. Yeah, you always do. Even though the 36 is technically mathematically closer to 40, I always will round down on my degrees of freedom so that I can make sure I keep that confidence level or significance level that I want. So we got to use 30, okay? Then we've got what else? We've got our test statistic of negative 3.17, but none of these numbers are negative. Oh yeah, because it's the absolute value. This chart is only doing the positive side, but the t distribution is perfectly symmetric, just like the z distribution. So what's to the left of negative 3 point blah, blah, blah would be the same as what's to the right of the positive version. So I want to find as close as I can get to that 3.17, and it's going to be positive. So it's between, am I on the right line here? This is my 30 line, okay. I'm getting between 3.03 and 3.385. Is that 3.17? So now trace that up. But those are not the ends, right? Why do you have to multiply them by 2?
Because it's on both sides.
Since it's not equal.
Right, good. Since this is a two-tailed test, since this is a not equal to test, then I have to double these and say my p-value is between 0.002 and 0.005. So again, if you have to use the table instead of your calculator, you're not going to get an exact p-value because you can't match your exact t on the table. But I can get an interval of values for p, which still will tell me if I reject or fail to reject. What would we do in this one?
Reject.
Why?
P is less than.
P is less than alpha, assuming alpha is 0.05. Yeah, good. Good. Okay, so I never use the table unless you guys use it on your test and you don't like your calculator, but I always use my calculator when I'm doing these problems. But I have to show you the table just in case. Sometimes they will ask questions where you have to use the table because they don't give you enough information otherwise. Most of the time, though, you could use your calculator. But just in case your calculator would die on the AP test, now you have a backup. Okay, so now with your calculator, what critical T star value has degrees of freedom 11 and probability of 0.05 to the right of T star? What would I do in my calculator? Second vars, if you have a TI-84 and do your inverse T, yes, I agree. Number 4, inverse T. If you have an 83, then go into your programs, and I should have given you that inverse T program. Okay, so what is our area? Yes, why is it 0.95? Good. Our calculator always goes from the left. The T table goes to the right, but our calculator always goes to the left. Okay, so our area is 0.95, and our degrees of freedom they gave us was 11. And so then I inverse T, and I get 1.796 for my T critical.
Nice.
Okay, so let me try that again. We did inverse T of 0.95, comma 11, because our calculator always goes left. Okay, and we got a T critical of 1.796. Gesundheit. Okay, so how about the last one? This one we just did too, but now we can get a real exact p-value from the calculator. So if we're testing the null hypothesis that the mean is 5 versus the mean is not 5 based on sample size 37 and get a t-value of negative 3.17, then how would we find the p-value of the test? Do I use inverse t again? No. TCDF, yeah. TCDF from what?
0 to from 3.17, negative 3.17 to 3.17.
Then you're going to have to do a lot more work after that. No.
Negative infinity to negative 3.17.
That works. Or make it positive and go to positive infinity. It's up to you. The way that I wrote it in your notes was to do the absolute value of z. So to make it positive 3.17 to infinity to a million. But then this is still not our p-value. I have to double it, multiply that by 2. But that works the same way as what Harrison said. You can take 2 times from negative infinity up to your negative 3.17 because you're finding both tails. So either way, you get the same value. Okay, so let me see what I got. If I do my second vars, TCDF is number 6 from positive 3.17 up to a million. Degrees of freedom 36. And I get 0.002 about. And then I have to, double that. So 0.003. And so we had said, if I go back to the slide right before, that our p-value would have to be between 0.002 and 0.005. It is. It's 0.003. It is between those values. But now I can have a more precise answer with my calculator than I can with the table. Yes, Will. Right, and then you have to take it times 2. Don't forget the times 2 part. That is what I had to before I doubled it. That's for those not equal to tests that you have to do the times 2.
And then you'll get it.
Have to do that times 2 if it's not equal to test. But in your calculator, if you run the test, it'll already take care of that times 2 for you. When it says p, it is your real p-value because you got to tell it what your alternative hypothesis was. So it already knows whether to double it or not. Okay. So now let's go through our steps in a one sample t-test for mu or mu sub d. This was where I was going to split it up into 2 parts, but I think we can handle it because it's just one word different. So steps in a one sample t-test for mu, or in parentheses, I put mu sub d. Steps in a one sample t-test for a population mean or mean difference. So again, we've got 5 steps for any hypothesis test. We just added 1 step from our confidence intervals. What is our step 1 for a hypothesis test? State the hypotheses. So they would be that what? Null hypothesis, right? U is equal to some number, or that u sub d is equal to some number. Oh, I can't see where I'm writing because the orientation's off. So then they go on top of one another. Can I move just that one? Okay. Maybe move a little bit. And then my alternative.
When mu is less than something, mu is greater than something, or mu is not equal to something.
Correct. So mu. I'm gonna have terrible handwriting on this because I can't see where I'm writing. Is less than, is greater than, or is not equal to. Or mu sub d is less than, greater than, or not equal to whatever our number is. Not gonna write those. Okay, there we go. And then step 2, name our procedure in context. So this would be a what? One sample t-test for mu or mu sub d, where mu or mu sub d equals the true mean or the true mean difference. Do you see for the mu sub d I put things in parentheses? The true mean height, the true mean difference in height, whatever it is, of all. I capitalized it. Maybe it will stand out more. So the true mean height of all AP Stat students. The true mean difference in true mean difference in sure.
Average height freshman year to senior year.
True mean difference in height senior year minus freshman year for all Free State students?
Yeah. Like,
Sure. That's a good one.
with the tractator function.
That's a good one. All right, then what is step 3? State and check our conditions. State and check our conditions. So we're still sinning. So what is our S? From, this is the part you guys are still leaving out. SRS from the population of interest or randomized experiment. Yep. Or if you're talking about mu sub D, you'd need to say somehow the differences are random. So like you guys had on the quiz, you were looking at the difference in growth for the Roma tomato seeds or something. So because the seeds were randomly chosen and randomly assigned to either the new fertilizer or no fertilizer, then the differences in growth are random. And our check, it has to be stated in the question somehow. Okay, just so you guys know that are going outside, I'm going to keep going. But the notes will be on my website.
I guess the most part is basically the same, right? But the terminology just changes the same.
Right. The math is a little bit different. The math step. Because you're not dealing with proportions. But, yeah. Mm-hmm. Okay, and so then our I for sin? Observations have to be, right, good. The observations or the differences have to be independent. So capital N is greater than or equal to 10 times little n. So the observations or the observations of the differences can be considered independent.
Question about normality a little bit. When we're saying that something has to be normally distributed, are we saying the sampling distribution has to be normally distributed or the sample distribution? Does it depend on
Not ever the sample.
Okay.
The true check is really kind of twofold. It depends. If it's for means, then you really want your population to be normally distributed, but it won't always be. And so then the central limit theorem would make your sampling distribution. So I would always be saying my sampling distribution.
Yeah.
But if I had to check my actual sample data for something, then I could say a graph of my sample, like a box plot of the sample data or a box plot of the sample differences is approximately normal. Therefore, the sampling distribution should be approximately normal.
Sounds good.
Okay, see you guys in 17 minutes. All right, so our N check then for normality, the sampling distribution of X bar is approximately normal. That's the stating. Then our check is, it could be stated in the question that the population or the population of differences is approximately normal. Or we could call into play the central limit theorem if n is greater than or equal to 30, because this is means. With proportions, we had to check our n times p naught and our n times 1 minus p naught. But when it's means, we can call into play the central limit theorem. Or a graph of the sample data or a graph of the differences is approximately normal. And maybe I should say, so therefore, the sampling distribution is approximately normal. Oops. No, undo whatever you just did. Okay. distribution. Okay. And we will practice these in just a sec.
Wasn't there something that if we're saying it's not a CLP, we had to say also?
Yeah, it's that same part. So should I put it in both sections?
What?
So the sampling distribution?
Okay.
I'll put it in both places.
You have to put it and then say therefore.
Uh-huh. Yes, just like that independence. Like 20 is greater than 10. Yeah, great. So what? What does that mean? Okay, so copy, paste. Okay, so it's there too. Okay. Yes, you do. So if the central limit theorem applies, because we're talking about means and because n is greater than 30, therefore then the sampling distribution will be approximately normal. Yeah.
And that's just on the analysis, right? Because that's up here.
Really, yeah, it is, except you don't have to if they say the population, but it wouldn't hurt anything if you did, because
Yeah.
if the population is normal, then your sampling distribution
Yeah,
will
so
be.
just in general,
Right.
that's it.
Right, yeah. Okay, we ready for the do the math step? My favorite step. All right, so our do the math. This is a T test, right? So we're not coming up with a Z statistic, we're coming up with a T statistic. But I get T the same way I got Z. I take my value minus the mean over the standard deviation. So my value was what I got from the sample. That would be my X bar, good, minus the mean from the null hypothesis. So I'm going to call it mu naught over the standard deviation, but now it's standard error because I don't know the population standard deviation. So I have to estimate it using my sample standard deviation, which is S over, good. Then I still have to do what else? State the degrees of freedom, which is just n minus 1. And same way, I can do my calculator, run the test, and it just hands me the p-value, which is how I do it. Or you can do TCDF. And if it's a not equal to test, then you have to do TCDF and double it. So I just run the test. And I can show you again how I do that in just a sec. And then my favorite part is over so fast, and we're back to lots of writing. What is step 5? Conclusion in context, right. Do you remember my phrasing from the other day?
Gosh, there's a lot of people like
You can go peek.
that. So many people over there.
Oh, holy moly. There's actually like a lot of people.
Why is it?
In a protest about the shooting in Florida last week, people are upset that schools are not doing more with how to deal with those crisis situations. Like, they didn't feel like their school was prepared. So it's just kind of a way to say, hey, wake up, we need better plans in place.
Right, I was gonna go out, but then I did.
But then you were like, wait, it's cool
So I
now.
was like, yeah,
Yeah.
sorry. There's only one S in conclusion.
Yeah.
And
In the
that's
word
on- that's on the recording.
They probably recognize your voice, but I won't point out your
Did you
name.
think that they would tree bucks?
So again, our conclusion in context, because the p-value equals whatever it equals, and then is, and I'll write it in two different colors, it could be less than, or it could be greater than. Oh, no, it's not going to let me write. Shoot. So temperamental. Seriously? Okay, what is your problem, Smartboard? Here we go. Okay, so our p-value, whatever our p-value is either less than or greater than alpha, whatever alpha equals. Right, I reject if it's less. If the p-value is low, the home must go. If it's greater, then you're right, I fail to reject. H naught. And you can really write H naught because the context is going to come in the next sentence. Let me say that again because that's important. This will save you a whole sentence worth of writing. You can write, because the p-value, whatever it is, 0.002 is less than alpha equals 0.05, I reject H naught. I literally write the letter H with the naught symbol, period. Because the context is going to come in the next sentence. There is, if you reject it, or is not, if you fail to reject, convincing evidence that, and then I steal the wording right out of the question. I will literally cut and paste on my computer, but steal the wording right out of the question. Context from question. Steal their wording. All right, you ready to try one?
Mm-hmm.
Okay. So, very fittingly, because I was running a fever yesterday, in the early 1990s, researchers conducted a study to determine whether the accepted value for, quote, normal body temperature, which is 98.6 degrees Fahrenheit, is actually accurate. Because most people, I think, run a little lower than that, like 97 point something. They used an oral thermometer to measure the temperatures of an SRS of 140 healthy men and women aged 18 to 40 at random times over a 3-day period. The resulting data consisted of 700 temperature readings. So, exploratory data analysis revealed several interesting facts about the data set. The distribution of the 700 temperatures was approximately normal. The mean of the 700 temperatures was 98.25 degrees Fahrenheit. The standard deviation of the temperatures was 0.73 degrees Fahrenheit, and 62.3% of the temperature readings were actually less than 98.6. And if the real average typical body temp was 98.6, how many would you expect to be less? And how many more? Yeah, you'd expect that to be the median. But it wasn't in this sample. So based on the results of this study, can we conclude that, quote, normal body temperature in the population of healthy 18 to 40-year-olds is not 98.6 degrees Fahrenheit? So, talk me through the steps. What is step 1?
I would personally say that hypothesis.
I would too. Actually, maybe I could write these instead of typing them. That might be easier. For step 1, okay. Our null hypothesis is
That mu is equal to
Good. Mu is equal to 98.6 degrees Fahrenheit. And our alternative, yeah, mu is not equal to 98.6. How did you get that it was not equal to instead of less than or greater than?
Well, it just says can we conclude that it's normal, not can we conclude that usually people are less than this or usually people are
Exactly. Yep. They just said not equal to. They didn't say less than, they didn't say greater than, they just said not. Good.
With the way they're wording the question,
Uh-huh.
like with the 62.3% or less than, unless it specifically states, are we still just going to say not equal to,
Right. Yes.
even if it like really hints one way?
Right. Because again, we shouldn't look at the data before we come up with our hypotheses. Our hypothesis should have been before we carried this out. So the question was, is it really not 98.6? Not, is it less than?
You know, you can see like there's probably more that
Mm-hmm. Or one guy that was dead and his body temperature was like 10. Okay. They didn't. They were healthy 18 to 40-year-olds. Nobody was dead. Okay. So, step 2, and I think I'm going to start typing, would be what?
Name procedure.
Yep. Step 2, name the procedure in context. This is a 1 sample T test. Good, not confidence interval. For mu. How do I get to mu? No, I don't think that matters.
They will take a point.
Oh yeah, that's a good.
Oh, here's some things I don't know my grading.
You don't need the dash. I thought we had Greek letters in here. None of those are mu though.
Oh, do the.
Well, crumb. Okay,
Just draw it.
I can copy paste from my other page.
Just draw it in black very neatly. So
I could draw it too.
Change the
Oh my goodness.
width of your pen to
of course.
Okay. Let me steal this whole sentence if I can. Copy. Why is my computer working so slowly?
It's probably because you're trying to record it.
Yeah, that's true.
I want to see if someone's like talking. I think everybody's just standing there doing nothing.
Well, that's the point of it, Harrison.
Well, I know. I should know if someone was like talking to them. Like someone was, you know.
Like chanting something. I think it's supposed to be like respect for like tradition.
Mm-hmm.
That's like the 17th
Yeah, I don't think it's like a.
It's not really
Oh, wow.
boundary right, it's like a respect right.
Just
It's,
find
yeah,
it
that's
because
really
it's
Okay, so 1 sample t-test for mu, where mu is the true mean, what?
And body temperature
Body temperature.
of all healthy adults aged 18 to 40.
Oh, I can't spell temperature. How do you spell temperature? E-R-A-T-U-R-E. Okay. Body temperature of all what?
Of all healthy adults aged 18 to 40. Is that it?
Yep. Adults age 18 to 40. Cool.
Oh, that's just to get everything after that.
Then, what is step 3?
Now we got it.
Yep, now we state and check the conditions. Okay, so for our S, we need an SRS. Oops, an SRS of, which is what? Body temps from healthy 18 to 40-year-olds. Or you could put this in your check part. You could just say SRS or randomized experiment. Maybe we should do it that way. And then put our context in our check part. Okay, an SRS or a randomized experiment.
You have to say it like from the population.
No, if I put it in my context, well, I don't know. Maybe that's a good thing because then will you remember to write it?
Yeah.
Um, of interest. Okay, and so then our check is it did say they did an SRS of, I don't remember how many people they had, and then they randomly took those people's temperatures a couple different times over 3 days. So they had a selection of 700 temperatures. They were both taken at random times and from a random selection of people. So they took body temp readings from a, hey, yeah, but come on in. What do you need? Oh, me? Okay. Finish that. You don't have to type mine, but finish yours.
You got it.
Is it still recording?
Yeah. And Mr. Hughes, what is the end of?
Please do not act as already inflated. 140 healthy men and women.
don't know when you should make it. Why actually like that? Yeah, always is.
It's gonna be a recording, guys. Stop it.
Okay. No one's gonna expose.
Yeah, people. Healthy 18 to 40-year-olds. Yeah. I'm here at 40. 18.
It's not only just about school treatment, brushing up on the different personality.
Do we have to say that it was also they took the temperature readings over a period of 3 days and randomized? Yeah, healthy 18 to 40-year-olds randomly.
Yeah, do you guys think that it's important that we mention
I think we're supposed to. But yeah, I think just to be safe. Over 3 days.
Okay, so they took,
Okay, so do you need to specify that it's like random, like the people are an SRS and the like readings were random?
it wouldn't hurt, but no, you probably just need to say the readings themselves were random.
Okay.
From an SRS of healthy 18 to 40-year-olds at random times over 3 days.
Therefore.
I don't think you have to say therefore. I said it was random. Say what the readings were. They took body temp readings from an SRS of healthy 18 to 40-year-olds at random times over 3 days. Do you have to say that at random times over 3 days part? Is that what you asked? I think you need the random times thing because it's the temperature readings that are important, not the people themselves. So it's the temp readings that need to be random. So I suppose if they just did it once for all those people, so you'd say since this was an SRS of people, then I can assume this is an SRS of body temp readings. But because they have 700 readings, which is more than people they had, I need to say those 700 are an SRS. So I think I have to say the random times. I don't think I have to say the SRS of healthy 18 to 40-year-olds. I just have to say they took body temp readings from healthy 18 to 40-year-olds at random times over 3 days. I think the first SRS is unnecessary, but the second random times is necessary. Does that make sense? Because it's the 700 that has to be random. And they only had, I don't remember how many people, let me go back. They only had, they only had 140 people. So if you just said they had an SRS of people, then you should only have 140 body temp readings. Does that make sense? And since there's 700 readings, I need to say they took them at random times over those days. Okay. So, now what happened to this one? Or I'm just going to type mu like that, where mu equals the true mean body temp of all 18 to 40-year-olds. Okay. I don't know what happened to that one, but now it's back. All right. Oh, because I put it over there. Oops. Oh, well. Delete. Okay. So then, oh, we're not done with our checks. I thought we were on to the math, but we're not on to math. I know. The checks take so long. Okay. So now we are on our I check. So we need, yep, independent observations. And how do I check that? Observations. Goodness. Okay. So capital N has to be greater than or equal to 10 little n, which is 10 times 10 times what? No, 10 times 700 equals 7,000. So then I can say because because we can measure body temps of healthy 18 to 40-year-olds more than 7,000 times. I can consider these observations independent. Healthy. Okay. And then what about our N? Uh-huh. Yeah, as long as you say sampling and not just samp, because then I don't know whether you mean sample or sampling. But dist, I think, is fine. So the sampling distribution of X bar is approximately normal. Good. Yeah. Well, it didn't say the population. It said our sample of 700 readings was approximately normal. So if our sample data is approximately normal, then it's likely our sampling distribution is approximately normal. Or, you're right, we can call into play the central limit theorem. Either one. So we could say it doesn't matter. It really doesn't matter. I'm going to put both of them in here. So I could say it is stated that the distribution of the sample data is approximately normal. So the sampling distribution will also be approximately normal. Or because n, which equals 700, is greater than 30, the central limit theorem, CLT, says the sampling distribution will be approximately normal, Either one. You don't have to write both. You just pick one. Whichever one you want. All right, now my favorite step. Yep. Now I forgot what was it 98.25 was the sample mean? Yeah, 98.25, standard deviation 0.73. Okay, let me see if I can remember all that. So for our do the math, we have to find our t. Remind me again, what do I do? Uh-huh. Right, which was 98.6. Right, you're dividing by the standard deviation of your sample over the square root of n, which makes it the standard error. And our sample standard deviation was 0.9 or 0.73, sorry, over the square root of 700. And then you can do this math longhand, I mean, and that with your calculator, or you can go into your tests. So if I want to do this in my calculator with the tests, I go into stat, over to tests. This is a T test number 2. T test number 2. And then it asks, do you have actual data or do you just have statistics? We have stats. So then it asks, what is your null hypothesis? 98.6. Your X bar, 98.25. S sub X, 0.73. N, 700. We said this was a not equal to test. I'm not going to change the color because I'm not going to graph. I'm just going to calculate. And I get a t value of negative 12.685. Come on, computer, what is your deal? No. No. It is a very small p-value. Good for reading all the decimal places out and going. Yes, I would too.
That hose down,
Okay, can I? No, right. And so p-value, I agree, I can say is approximately 0 because it's really 2.477 times 10 to the negative 33rd. You've got to watch the scientific notation on p-values. Think about what a p-value is. A p-value is a probability. It can't be more than 1. So don't try and write down a p-value of 5 point something or 2 points. That doesn't make any sense. Think, look for your scientific notation. Okay, we're still missing something in order to do the math.
Yeah.
We have to state our degrees of freedom. What is our degrees of freedom?
699.
Good, it is. 700 minus 1 is 699. Cool. Okay. Do you want me to show you how that math would work the old-fashioned way?
No.
We don't really have much time, but I could. Okay. You're okay with doing the test in the calculator? That's the way I like to do it too. Okay. Then one more step. We have to write our conclusion in context. Good. Did I give myself another page for that? No. Add a page. Okay, so my conclusion in context is what? Because the p-value, good. Because the p-value is, I don't know how to do approximately on here. Can I do this? Is approximately 0. Because the p-value is approximately 0 is less than alpha, which equals, they didn't say. Good. I reject or fail to reject?
Definitely.
Reject. That p-value is so low, it's pretty much 0. I reject H naught. Period. You do not have to put that in context here, because we're going to put the context in the next sentence. So just literally write the H naught. So there is convincing, significant, whatever, it's fine. Convincing evidence. Oops. Evidence to conclude. And then let me go back and steal their wording. If I can get to it. Okay. No, go back. Oh, come on, computer. I hate that little spinning wheel. Nope. Shoot. I wasn't patient enough. Okay. Copy. To conclude that normal body temperature in the population of healthy 18 to 40-year-olds is not 98.6. Got all the same font. Yeah, they did this in the 90s. Yeah, but somehow in the real world, yeah, it hasn't changed. You could say either way. You can use the context that they gave you, or you could say to conclude that the normal body temperature, or you could say mean body temp for all 18 to 40-year-olds. For all healthy 18 to 40-year-olds, that's important. Either is okay. Either is okay. I like to stick with that all because then you remember it, but I also steal the context of their questions a lot too. Uh-huh. No, because they said the word population. That means all.
Yeah. If you do avoidance tasting, if you do command shift, then it will do it in the format.
That totally makes up for the 2 S's in conclusion statement. That's awesome. What was it? Command Shift V?
Yeah, I'm pretty sure.
It keeps the formatting? That is
Yeah, so
cool.
like since you still have it copied, right? If you go to the end and get that, I'm pretty sure if you hit command shift.
Okay, let's do it just real quick for fun. If it will do it real quick. Okay, so if I do Command V, it does that. And now if I go back into here and do Command Shift V, it doesn't do anything. It could also be that, you know, my computer's not working very well today. And
I know there is a way
okay,
to
to keep the formatting. That's cool. I did not know that.
It's like,
Well, at this point,
Yeah, you have like a vendetta.
All right, guys, we're going to run out of time. Oh, now it won't undo that. No, it was a good thing. I just don't know how. Okay, we're just leaving that extra sentence at the end because it won't let it go. Okay, so hang on. I hadn't gotten a chance, because that was something else I was going to do this morning, to look at these problems. Okay, but then I have to look at the other problems too. Okay, hang on. Just don't write down the homework yet, because I have to look at the other problem numbers too. Okay, so then let's try to go through another test really quickly for the mean difference. So, most automobile tires are inflated with compressed air, which consists of about 78% nitrogen. Aircraft tires are filled with pure nitrogen, which is safer than air in case of fire, because oxygen obviously burns. Obviously, that feeds fire. So, could filling automobile tires with pure nitrogen improve safety, performance, or both? Consumers Union designed a randomized study to test whether nitrogen-filled tires would maintain pressure better than air-filled tires. They obtained 2 tires from each of several brands and then randomly chose 1 tire in each pair to fill with air and 1 with nitrogen. All tires were inflated to a pressure of 30 pounds per square inch and then placed outside for a year. At the end of the year, they measured the pressure in each tire, and the amount of pressure lost in pounds per square inch during the year for the air-filled and nitrogen-filled tires of each brand is shown in this table. So there's all of our data. And then, do these data give convincing evidence that filling tires with nitrogen instead of air decreases pressure loss? So, what do we need to do for step 1? Hypotheses. What would our null hypothesis be? The mean difference would be equal to, no, that's what I'm writing. Mu sub d is the mean difference is equal to what value, what number? You're assuming that everything's the same until you prove it out. Yeah, good. You're assuming that there's no difference between air and nitrogen. Right. Until you find evidence that there is. And so this said loss. So I wrote it as mean difference is less than 0. But then I have to be careful about how I subtract in my context. This time I used capital D's. You can use lower D's. It doesn't matter. Unless they specifically say, like, there's a difference of 2 inches between, I don't know why they would do that. Yes, it's usually going to be 0. But feasibly, I could come up with wording that would be different.
You mean difference between 18-year-old male and female?
Then you're to a 2 sample. Then you're not looking at the difference. Unless they were, like, somehow paired, like boyfriends and girlfriends.
Twins.
Okay, twins. Then you could.
Alright, so you take this, right?
Uh-huh.
Command copy, and you just paste. It's like that. Then by command shift paste. It goes.
Cool. Huh. I don't know why it wouldn't do it for me. Probably just because my computer's freaking out, but thank you.
It does work.
I will do it again later. Definitely. Okay. So, step 2. What time do we get out of here, guys? 45? Oh, geez. I'm just going to show you then. This would be a one sample t-test for mu sub d, where mu sub d is the mean difference. Now you have to be careful about which way you subtract. I said nitrogen minus air in tire pressure for all brands of tires. Then our step 3, of course, would be to sin. It's stated that this was a randomized experiment. They randomly decided which of the 2 tires got the nitrogen and which one got the air. So the differences in tire pressure are random. Notice I underlined that. I don't know why I underlined some and italicized others, but anyway. We need our observations to be independent. So since there were 31 different pairs of tires, then there are 310 differences. Just like on that seeds one, I think there were 120 differences. Like there were 12 different measurements. And so then there were 24 seeds, but there were 12 differences in plant growth. Same thing here. There's 310 differences in tire pressure. So we can assume that because there are more than 310 pairs of tires in existence, the differences are independent. We need the sampling distribution to be approximately normal. Since n is 31, which is greater than 30, then the central limit theorem says the sampling distribution of the differences will be approximately normal. See how I kept saying differences in every single check? Then, I don't know if I have the math step in here. Let's see. Oh, I kind of do. To calculate our t, we would take our sample mean, which we could just put all the data in our calculator, and when we run t-test, tell it data. And then you could do your list 1 minus list 2 and put them in list 3, or you can tell it list 1 minus list 2, whatever. Our null hypothesis was 0. The sample standard deviation, again, your calculator will give you when you run the test, over the square root of 31, that comes out as negative 5.797. And so then my p-value, because this is strictly a less than test, is just the probability that t is less than that value, which again came out to be about 0. And I state my degrees of freedom. So because the p is low, the hoe must go. Because the p-value, approximately 0, is less than alpha, assumed to be 0.05. Again, they didn't give me a value. I reject H0. There is evidence to conclude that filling tires with nitrogen instead of air decreases pressure loss. Or you could say there is evidence to conclude that nitrogen over air will decrease pressure loss in all tires, if you want that word all in there. Okay, so now let me look at this homework super quick. But there was no change. Okay, that's a two-sided. All right. And then what's this one? That one has data. Okay, how about this? Yeah, I'm putting them together. Let's do page 745, 1, 2, and okay, and 4. And then on page 754, do number 9, A, B, and C. Okay, so I can put these together on here. Page. What was the first page?
745.
745, number 1, 2, and 4. And then page 754. Okay. It's actually on 759. 9 ABC. Okay, there we go. That's what I want. Okay, now we should be able to stop recording.